I'd like to talk a little bit about peptide sequencing. Let's say we've got a peptide. This one has 5 amino acids making it up, so it's a pentapeptide. And what we can do is we can figure out what the structure of the peptide is if we can order these or find the order of these amino acids in the peptide. That's called primary structure. Now what you might want to do is say, well, okay, why don't we just go ahead and hydrolyze everything? That is, we just break apart these peptide bonds. And we can do that if we use very strong acid and heat. We can break them up into their component amino acids. But unfortunately, if we do that, while we can figure out what the amino acids are by ion exchange chromatography, we'll never know what the order was in the original peptide. So what we've got to do is look at some ways that we can manage that. And we can do that using, first of all, the Sanger reagent. What the Sanger reagent will do is it will react with the amino end of the peptide, which is the first amino acid in the chain, and it will break that amino acid off the chain, and then you're left with this kind of compound, which will actually fluoresce at a unique frequency depending upon the amino acid that's connected to this grouping. So what that allows you to do is actually, looking at the fluorescence frequency, will tell you what is connected at this point, which will tell you what was on the end of the peptide. That will tell you what was first in the peptide chain. So the Sanger reagent will allow us to do that. Cyanogen bromide is a chemical treatment that allows you to cut an amino acid peptide chain specifically after methionine. So if you reacted this peptide with methionine, it would break after methionine, leaving this peptide plus valine. Just to give you a very brief look at the reaction itself, you can see it's a chemical process that specifically interacts with the methionine side chain. That's what the side chain looks like here. And then it breaks the peptide apart at methionine, but just after the methionine specifically. Right, there's 2 others I want to talk about, and those are chymotrypsin and trypsin, and these are enzymes. And they cut specifically after certain amino acids in the structure. Chymotrypsin will cut after PHE, TRP, and TIR, so it'll be phenylalanine, tryptophan, and tyrosine, specifically after those. Just to give you a very brief explanation on what these do as enzymes. If you've got an enzyme here, it's going to take some sort of substrate, and the substrates in this case involve these particular amino acids for chymotrypsin, phenylalanine, tryptophan, and tyrosine. And you get this activated complex. The thing though is that the enzyme has a specific shape in this what's called the active site, and it will only take certain things of certain shapes. I want to show you what this looks like with regard to the amino acids. And let's look at phenylalanine, tyrosine, and tryptophan. And I want you to see that the side chains are fairly similar in structure. So those are the ones that will specifically fit into this hole in the enzyme. So then what happens is that the enzyme will cause this to break apart, and then you get the enzyme back in its original form, plus products from the reaction. And the products from this particular process will be the peptide chains that are broken apart. So this will cut specifically after these. So there's a TYR, it'll cut after that. You'll be left with these 2 peptide chains as products. Now trypsin is specifically used to cut after arg and lys, so arginine and lysine. Let me show you what that looks like. And arginine and lysine are down here, and you can see that those 2 side chains look fairly similar as well. And that works pretty much in the same way, except now these are specific for arginine and lysine residues after and they will cut after those in the chain. So here's an ARG here, so it'll cut after the ARG, and you'll be left with these two peptides right here. Alright, so that's what all that stuff will tell you, and we can use this information to actually sequence a longer peptide, and I'll show you an example of that in a minute.